Good morning, folks. This is Mike coming back at you with another video on Foundations of Math 2. In this video, we are going to talk about using permutations and combinations to determine probabilities, theoretical probabilities of events happening. We talked in previous videos about how to calculate permutations and combinations. So now let's use these things to figure out some probabilities. So first problem up, you have to pick 3 books at random from a pile of 15 books, 8 of which are textbooks and 7, the other 7 being novels. What's the probability that all 3 books that you pick are going to be novels? Now, one of the trickiest parts to these problems is figuring out whether you have to use permutations in the problem or you have to use combinations. And really, to figure out whether you have to use a permutation or a combination, you sort of have to think about the context of the problem that you're in, and you have to think about, does the order in which I pick these things really matter or not? Here, we have 15 books. We're picking 3 of them. The probability is that all 3 books picked are novels. It doesn't say anything about the order in which we have to pick them. If our question was, what's the probability that you pick a novel and then a textbook and then a novel, okay, then there's some order there that matters, and then perhaps you'd be thinking, okay, order matters, permutation. But here, for our question that we have, it just says all 3 books that are picked are novels. Doesn't say anything about picking anything in any kind of order, so that means we're going with a combination here. So again, we're calculating the theoretical probability. Here's my event E. All 3 books being picked are novels. So P of E, again, theoretical probability is the number of outcomes that are in the event divided by the number of outcomes that are in the sample space. So first, let's go with perhaps the easier one. In fact, they're both kind of on the same level as in terms of how hard they are to find. They're both really not that bad. The number of outcomes in the sample space. Basically, how many ways can we pick 3 books from this pile of 15? And once again, the order in which we pick these books does not matter. What ultimately matters is what 3 books we have. So basically what we're saying is, how do we choose 3, or how many different ways can we choose 3 books from a pile of 15? So the total number of possible outcomes is going to be 15 choose 3. On top, the number of outcomes that are in the event E. Again, the event is that all 3 books picked are novels. Well, of the 15 books, 7 of them are novels, and we want to know how many ways can we choose 3 of these 7 novels. So basically, the number of outcomes in the event is going to be 7 choose 3. All right, so let's pull out our scientific calculators and let's figure out what these numbers are. We talked in one of our previous videos about how we do combinations in our calculator. So I'm going to do 7, go to PRB, go over to NCR, and then hit 3. That's going to give me 35. And now we're going to do 15, choose 3. And 15, choose 3 is going to be 455. So the probability that we have all 3 books that are picked being novels is 35 over 455. Again, typically we simplify these things out as much as possible, and that is 7 over 91, or that is also 1 over 13. So we have a 1 in 13, or a probability of 1 over 13 that the 3 books we picked in this case are novels. So there is a little bit of thinking here that you have to do in these problems here. You do have to think, okay, does the order matter or does it not? If the order does matter, then chances are permutations are going to come into it in some way, shape, or form. If the order does not matter, then you're going with a combination. Second example here, what's the probability of being dealt 4 kings in a 5-card hand from a standard 52-card deck? This maybe is something more relatable to more of us, those of us who play cards with friends or family. What is the probability of being dealt the 4 kings in a 5-card hand from a standard 52-card deck? Again, first thing you should think of, does the order of the cards in my hand necessarily matter? No. We don't care what order the cards are dealt to you in. We only care about what cards there are. So this means that combinations are going to be used here. Being dealt the 4 kings in a 5-card hand, that is our event E. Again, the probability of E happening, the theoretical probability, total number of outcomes in the event divided by the total number of outcomes in the sample space. The total number of outcomes in the sample space. We have a standard 52-card deck. We can be dealt any 5 cards whatsoever. But again, the order in which we get the cards doesn't matter. It's just what 5 cards we get. So the total number of outcomes we can have, or the total number of 5-card hands we can have, is going to be 52, choose 5. That was the easier part of this. What's less easy, perhaps, to figure out is how many outcomes are there in that in the event E that we want. So, how many different ways can we be dealt 4 kings in a 5-card hand? So if I look at my 5-card hand, well, 4 of these 5 cards have to be the 4 kings. And since the order doesn't matter, there's only one way that we can come up with the 4 kings, because there's only 4 kings in the whole 52-card deck. So basically, we're being dealt all the kings. There's only one way that can happen, is if you deal all 4 kings. So there's only one way that we can get those 4 cards happening. The 5th card, though, is essentially free. This card right here, it can be whatever we want it to B. We have the total 52 cards, but we've already been dealt 4 of them, namely the 4 kings. So if we take 4 cards out of that 52, we have 48 cards left over, and we can be dealt any one of those 48 cards. So there's a card, and there can be 48 of those that can take that spot. So if I do 1 times 48, that gives me 48. So there's 48 different hands that we can have that will have 4 kings. So maybe at first that seemed a little bit more complicated to understand. Maybe it still is, maybe slightly. But if you just pause, slow down, think about it, you'll see that that does make sense. There are only 48 hands, or 48 5-card hands that you could be dealt that will have all 4 kings. So our probability then is 48 divided by 52 choose 5. Question is, what is 52 choose 5? Well, if I go again, 52, choose 5. I'll set this down so you can actually see it, and it's flat on there. Ooh, 52 choose 5, 2,598,960. So 48, as we said, 48 over 2,598,960. Yes, typically we would like to simplify these out more, and you can. But when it comes to large values like this, sometimes it's more interesting to look at it as a decimal. If I do 48 divided by 2,598,960, I get 0.000185 approximately. So that is your probability that you get the 4 kings as a percentage. This is 0.00185%. In the world of cards, and say you were at a casino and you were dealt this hand, they might think that there is some kind of cheating happening if they know their probabilities and their percentages, because this is highly, 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 highly unlikely. Not to say that it can't happen, but it's incredibly unlikely that this would. So the last problem that I want to go through here with you is actually kind of a famous problem in the world of math and probability. This is a really neat problem just to sort of stir in and perhaps think on, just because it's a neat little thing to think of. It's referred to as the birthday problem. This particular one, what's the probability that given 4 people in the same room, at least 2 of them have the same birthday? And we can generalize this to any number of folks. 10, 20, 50, 100, whatever. What's the probability that given a certain number of people in a room that at least two of them have the same birthday. So let's first think about the way that, or how many ways, and thus what's the probability that everyone has a different birthday. And then what we'll do is we'll take that probability that we find and we'll subtract that from 1, because you either have everyone having a different birthday or you have at least 2 or more people having the same birthday somewhere. So let's find probability of difference birthdays for these 4 people. Okay, so we have our 4 people. We want to know what are the chances that they have, or what's the probability that they have different birthdays here. Well, for the first person, you can have one of 365 days. Doesn't matter what the birthday of the first person is, we have to start somewhere. We go to our next person. If we want to find, in the end, the probability that they have different birthdays, then the second person can't have the same birthday as the first person. So the birthday of the first person has to be thrown out. And thus there are 364 possibilities, not probabilities, possibilities for the birthday of the second person. Third person. Okay, the birthdays of the first and second people can't be possible then. So there are 363 possible birthdays that will work for this third person. And then you can probably guess 362 possible birthdays for the fourth person. So the total number of ways that we can have the different birthdays here that will work: 365 times 364 times 363 times 362. Those are the total number of outcomes that will work. What about the total number of possible outcomes in the sample space? Just overall, how many different ways could we have these birthdays for these 4 people? Well, the first person can have 365. The second person, in theory, can have any one of 365 birthdays. And similarly for the third and the fourth. So it's 365 times 365 times 365 times 365. That bottom is 365 to the 4th power. And the numerator there we can actually represent as a permutation. The top is 365p4. If you go back to the formula for a permutation of n objects taking r of them at a time, and if you use 365 for n and 4 for r, you will get, when you cancel out things, this right here. So this is the probability that these 4 people have completely different birthdays. And if we plug this into the calculator, I can tell you right now we're going to get some ugly looking numbers. Some very large numbers. But in the end, we get something we can actually work with. So we get approximately 0.9836. So that's the probability that 4 people in a room will all have different birthdays. So we said at the beginning of this question, to find the probability that at least 2 of them have the same birthday, I'm going to take this probability that I find, subtract that from 1, and then what I get left over, that's going to be the answer to my question. So therefore, the probability that there's the same birthday between at least 2 people in this room with 4 people is going to be 1 minus the probability of different birthdays. So 1 minus 0.9836. That is 0.0164, or 1.64%. So that is your probability that at least 2 people in the room will have the same birthday. Now, obviously, the more people you have in your room, the greater the probability that at least 2 people have the same birthday. And it doesn't take a ton of people to start having the probability that 2 people have the same birthday to start to become fairly large. If you have 3 people in the same room, then the probability that at least 2 people have the same birthday is 0.7063, or 70.63% chance that 2 people in the room have the same birthday. And if you have 50 people, then the probability is 0.9704. So 97% chance that 2 people in that room will have the same birthday. So not as unlikely as you may think, given the number of people that are in a room. But guys, this concludes our video on calculating probabilities using permutations and combinations. Again, big thing here is looking at the context of your problem and seeing, okay, do I need a permutation or do I need a combination? Does the order matter or does it not? If you have any questions, please be sure to reach out to me, guys. Emails, voicemails, texts, phone calls, flare signals, SOS bonfires on beaches, telepathically getting into my mind and saying, help me, whatever you have to do. Otherwise, until the next video, take it easy, guys.